In this video, we will look at quantum numbers, Hund's rule, probably just Hund's first rule and Hund's second rule, but we'll likely just call them Hund's rule, and Pauli Exclusion Principle. And the level of this video will be for a good general chemistry class. Okay, so quantum numbers. Quantum numbers, there are many quantum numbers. There are typically 4 that you'll need in a general chemistry class. And before we look at the quantum numbers, what are they? They are whole number integers that can be used to give an address or a description for a subatomic particle. And in chemistry, we're relating that subatomic particle to the electron. Okay, so we have lowercase n, which is known as the principal quantum number. It's also known as the period number in the periodic table. It's also called a shell. So these are all synonymous, they all mean the same thing. And finally, it's also the energy. So once we know the principal quantum number, we know its shell, we know its period number, we know its energy. N can have values, whole number values, so it can be 1, it can be 2, it can be 3, it can be 4. Whole number values begin with number 1. The second quantum number we'll look at is L. L is called the orbital angular momentum quantum number. It's also known in Europe typically as the azimuthal quantum number, but in the US more frequently it's called the orbital angular momentum quantum number, and it's also referred to as the subshell. So as the word suggests, there are numerous subshells within a given shell, and so we'll keep a lookout for that. L can have values of 0, 1, 2, all the way up to n-1, where n here refers to the principal quantum number here. It's a good idea at this stage to memorize the following table, as it will be used frequently moving forward. So if we put a plot or a table of L values, so 0, 1, 2, 3, 4, 5, 6, we could keep going. You'll realize there's little point to keep going too far in a second. If we look at the orbital, and then finally we're going to look at the shell, then we see that the orbital for an L value equal to 0 is an s orbital. P has an L equals 1, D has an L equal 2, F has an L equal 3. And these are the s, p, d, and f orbitals that we're used to in the periodic table. If you recall the structure of the periodic table, you have the s, p, d, and f blocks in the periodic table, and this is where they come from. We'll see later, these names, they're not logically named, they're historically named. S is named after sharp. So we have sharp, principal, diffuse, and fundamental. Again, they're historical in origin, not logical in origin. Following the F orbital, they just become lettered alphabetically. So we would theoretically have G, H, etc. And typically we miss I because I is used for as an imaginary number, and for that reason we tend to avoid I. Okay. So the shell, we start off, now these are lowercase letters, the shells are uppercase letters. We start off with uppercase K, the K shell, and then L, M, N, then alphabetized O, P, Q. Why the shell starts with the letter K? To be honest, I'm not 100% sure the origin of K. I've never really looked into it myself. I just accept that it starts with K. So there's unusual honesty for you. There are two more quantum numbers, so let's erase the board and then we'll put them on so that we can put them on the same board. The third quantum number is ML, lowercase m, subscript lowercase l. This is called the magnetic quantum number. And as you might expect, it tells you if something is magnetic or not. We won't look at that in general chemistry, but that's what you could use to look at in a subsequent course. ML can have values between plus and minus L, including 0 at the midpoint. So it can range from negative L plus 1. So we go from a negative L, not 1, negative L, then we add 1, so negative L plus 1. We would add another 1, you sequentially add 1 at a time till you hit 0, and then you keep going to make it symmetric the other side. So positive L plus 1, well, that would be positive L minus 1, positive L. So again, it should be symmetric both sides. And there are 2L plus 1 values of ML. And you can see that, so for example, if L equals 1, 2L plus 1 is going to be 3, and that would be negative 1, 0, and plus 1. If L equals 2, then 2L plus 1 values are 5. So 5, and they would be negative 2, negative 1, 0, plus 1, plus 2. So it's always symmetric. I'll, in this video, tend to have negative on the left. It doesn't really matter. You can have negative on the right. You'll still get the same outcomes, as we'll see. So it really doesn't matter which way you do it. And the fourth and final quantum number that we'll need in general chemistry is ms. ms is the spin quantum number, m subscript s can have values of plus or minus 1 half. So plus or minus 1 half. And this has a significance for chemists and for physicists. If you have a subatomic particle like an electron with a spin, a half-integer spin, or a multiple of a half-integer spin like we do here, it implies it's a fermion. After the physicist Enrique Fermi. So it's a fermion or a Fermi particle. And what does it mean to be a fermion? It means that you obey Pauli Exclusion Principle. And we'll be coming to Pauli Exclusion Principle a bit later. So our electrons have to obey Pauli Exclusion Principle. And although we won't be looking at the proton and the neutron in this video, the proton and the neutron are also fermions and they too obey Pauli Exclusion Principle. And the consequence of that is it can't be overstated. That's how important it is. Okay. So we'll now get to look at in a bit more detail at the Pauli Exclusion Principle. And I'm going to see if I can pause the video while I erase the board and see if that works. Well, apparently that worked, so I'll know to do that in future. Okay, so now we're going to look at Pauli Exclusion Principle. I forgot to change the heading though, so change the heading to Pauli Exclusion Principle. As we go through this material, I would keep in mind how absurdly different this material is compared to regular classical mechanics. I think too many students, they'll get bogged down with the details and the math, and they end up avoiding the subject, and they don't see the inherent beauty of the subject, the mystery of the subject, and majesty of the subject. So sit back with your notebook and a pen and enjoy how absurdly unique quantum mechanics is. So I'll keep that in mind as we go along. Pauli Exclusion Principle. This was theorized by the late and great Wolfgang Pauli. And as far as I know, this was a solution, a theoretical solution, rather than Wolfgang Pauli had no proof. It was just an idea that he came up with to explain a phenomenon a priori. I think that's the historical route. So consider two electrons. Consider two electrons, and as we've previously mentioned in another quantum mechanics video, we're going to view the electron as a wave function which has the symbol psi. So we're going to label one of these electrons psi 1 alpha. We'll label the other one psi 1 beta. So psi 1 alpha and psi 1 beta. Okay, and we'll make some assumptions. Let an electron be represented by its wave function psi, which is spelled at least psi, so it's a Greek letter psi. Consider two electrons as we've considered here. They have to be in the same atom. So this could be an atom, it just could be a locality, but they have to be next to each other. They have to appreciate each other as there. So consider two electrons. One electron is in state alpha and the other is in state beta. So this is our diagram here to orient you if you're unfamiliar. So Wolfgang Pauli theorized. So he was a smart individual. He also had common sense. He knew that the world existed. So how could the world exist? What kind of conditions are needed to make the world exist if the world is made of fermions? And we'll see what that means now. Pauli theorized that for such a system to exist, and persist, so not just exist for a moment, it must obey the following. So the whole system has an uppercase psi. So the capital psi is going to be the sum of all of the psi's. So this whole system is uppercase psi. And it consists of the wave function of electron 1 in state alpha, as a product of the electron function of electron 2 in state beta. So the wave function of electron 1 in state alpha multiplied by the wave function of electron 2 in state beta minus the wave function of electron 1 in state beta multiplied by the wave function of electron 2 in state alpha. So this is the equation. He said, okay, I'm going to invent this equation. He didn't actually invent it, but he applied it. He applied this equation to explain how this exists. It looks very daunting if you've never seen anything like this before, but we're going to break it down into a very... we're going to try and interpret it and try and make it a bit more concrete. First of all, we notice that this equation, if you're familiar with the mathematical structure of this equation, it's a determinant equation. So what's a determinant equation? A determinant equation is a concept from matrix mechanics, or matrices in general. And if you take a square matrix, which basically means has the same number of rows and columns, the determinant equation for that square matrix is the representative equation for the entire matrix. So just a brief aside on this so that we can follow along and appreciate this equation. Let's look at the determinant of a 2 by 2 matrix. And then we'll see it here, and then we'll see, oh, that's a determinant equation. So that'll be the point. We take a matrix, which is just a collection of information. So let's say the matrix has the value A, B, C, and D. So we've got a matrix with 4 values, a collection of values. We have rows going left to right, and we have columns going top to bottom. If we take the determinant of this equation, we put it in parallel lines. So the determinant of this 2 by 2 equation is the diagonal AD minus the opposite diagonal CB. So now you can see that this is just a determinant equation. We've got a product minus another product, a product minus another product. And in a second, I'll erase the board and we'll actually write our system here, our 2 electrons, as a matrix equation. So we can really get a grasp on what this equation is. Okay, we've just seen that we can write a 2 by 2 matrix, and we've had a little brief aside on what a 2 by 2 matrix looks like, and we see that it produces, or you can produce, a determinant equation from it. So let's take our Pauli equation to explain the previous diagram, and let's write it in our matrix form. So this would be a 2 by 2 matrix, or a 2-dimensional matrix, and I'd have psi 1 as a column, I'd have psi 2 as a column, and then I'd have the 2 psi 1s, I'd have different labels, so I'd have the alpha label and the beta label, the alpha label and the beta label. And then we can see, if we take the determinant, I'd multiply psi 1 alpha by psi 2 beta, psi 1 alpha by psi 2 beta, and then I'd subtract the opposite diagonal, psi 1 beta by psi 2 alpha, psi 1 beta by psi 2 alpha. Okay, so now you're familiar a little bit more than you were previously about determinants. And again, this represents the matrix, it's the representative equation. So Pauli reasoned that if this equation is true, and it has to be true, the state labels alpha and beta have to be different. We'll see it was an a priori assumption. Let's see what the assumption plays out to give us, and then let's think about what a lack of this assumption would lead to, and why we don't need to bother with pursuing that any further. So Pauli reasoned that state alpha must be unique from state beta. Again, beta and alpha are just labels, but they have to be unique. They can't be the same thing. Alpha can't mean beta. He reasoned they have to be unique since the consequences of the opposite assumption would lead to the collapse of the universe. So this is not what we've seen yet. We live in a universe, we can see it, we're in it. The universe hasn't collapsed yet. And this is the only way to stop it collapsing, if those labels are not the same. So let's see what happens when you set them the same. So in opposition to what we've said, let's state alpha equals state beta. If this is not to be done, let's try it. Let's see what happens. Let's state alpha equals state beta, and let's see what happens. Well, that would mean when we calculate our total psi for the system, then I would write psi 1 alpha, psi 2 beta, minus psi 1 beta, psi 2 alpha. So my equation. Now let's rewrite it where I can either write all alphas or all betas because the label doesn't matter, they're the same. So to be consistent with my notes, which I'll upload and make available to my students, psi 1 alpha, psi 2 alpha. Here I've just said that since alpha is beta, I'm just going to write alpha everywhere. Minus psi 1 alpha, psi 2 alpha. So alpha and beta are the same. Let's just write alpha everywhere. You could do the same with beta. Well, now I've just got the same thing subtracted from itself. So it would lead to 0. So if the labels don't matter, then the total psi for our system sums to 0, and 0 is bad. That means that our system, our subatomic particles, the electrons, it could be the neutrons or the protons, they have no quantum information, which means they don't exist. That's bad. That would lead to the disappearance of the entire universe. So the labels have to matter. So hopefully that's pretty dramatic evidence that the labels have to matter. So clearly alpha and beta are different. When I teach this in a physical face-to-face class, when we're not going through this COVID-19 pandemic, so usually I would then talk to the students about, if the students are sat in a lecture theater, you all occupy a seat, and let's assume that you're not allowed to sit in anybody's lap. Then every occupant in that room takes up information. You would have to describe the location of every person in that room. And then somebody new coming into that room would no longer be able to be described, would no longer be able to sit in a chair that a student's already sat in. Because if they could, their location would be described by the same information. The state of that student would be the same if they were allowed to sit on each other's laps. And even then, that wouldn't be the same, because sitting on each other's laps is not being in the same location. You would literally have to ghost morph into the body of the other person, and clearly people can't do that actually for this same reason. Because we're made of protons, neutrons, electrons, and these subatomic particles can't do it, so the collection of them, us, can't do it either. So labels are important. They stop the universe collapsing. Okay. So a bit later on, we'll see how we can execute this in practice in a chemistry setting. But I'll just leave you with this vernacular way to think about it. So Pauli's exclusion principle essentially says that no two subatomic particles, in our case electrons, so fermions in general, but we're interested in electrons in this instance, can have identical sets of quantum numbers if in the same atom. obviously, if you have 2 carbon atoms, the quantum description is identical, but all 6 electrons in each carbon atom has unique sets of quantum numbers. Otherwise, there would be no such thing as the atom itself. Okay, so in a nutshell, that's Pauli. So we'll get rid of this board, and then we'll move on to looking at making a connection with this to the periodic table. So having looked at or introduced the 4 quantum numbers, having introduced Pauli Exclusion Principle, let's now make a connection with the periodic table and ground it more in terms of what's useful to a chemist. So we'll call this linking quantum numbers with the periodic table. Linking the quantum numbers with the periodic table. So we've said already that the magnetic quantum number, ml, we've said that there are 2l plus 1 values of ml. And if we apply that fact to s orbitals, so for example, I'm going to call it s electrons. Now I have to be careful here. Electrons don't know or care if they're in an s orbital, a p orbital, a d orbital, or an f orbital. Electrons are quantum mechanically identical to each other. So when I say an s electron, I really mean an electron in an s orbital. But so just to clarify, that's what I mean, but I'm going to write s electron anyway. For s electrons, the orbital angular momentum quantum number was 0. So we've seen that in a previous diagram. So there are 2 lots of 0 plus 1. So there's 1 value or 1 ml value. Now the 1 ml value implies 1 orbital. And actually, I guess 1 s orbital. Okay, so we're trying to see the connection between these quantum numbers and the orbitals. So why is there only 1 s orbital? Because of this fact here. For p electrons, or electrons in p orbitals, but I'll continue to call them p electrons because I think it's useful, although you have to be careful with what you think it means. L equals 1 for p electrons. So there are 2 lots of 1 plus 1, which is 3 ml values. And those 3 ml values imply 3 p orbitals. So why are there 3 p orbitals? Because there are 2l plus 1 values and L is 1. Why is there 1 s orbital? Because there's 2l plus 1 values and L is 0. For d electrons, L is 2. So there are 2 lots of 2 plus 1, which is 5 ml values. And those 5 ml values imply 5 d orbitals. And then to conclude the periodic table, we have F electrons. So for F electrons, L is 3. So there are 2 lots of 3 plus 1, which is 7 ml values. And those 7 ml values imply 7 f orbitals. So I'll erase this. I'll construct a diagram that's going to be useful to you, and I'd encourage you to construct this diagram in any assessment that you do looking at quantum numbers. So we've just seen, or started to see, a connection between the quantum numbers and the periodic table, which is what we need to get to in general chemistry at least. The following diagram is pretty useful, and it's a good visual when you're trying to solve some quantum number questions in an assessment. So if you draw a pyramid, where the pyramid is going to be a symmetric pyramid, so a stack of 4 in the middle, and then a stack of 3 on either side, then a stack of 2, and then finally a single on the end. So we draw a pyramid like this, and then the boxes represent the orbitals. We said that there was one s orbital, we said there were 3 p orbitals, we said there were 5 d orbitals, we said there were 7 f orbitals. And now we're going to superimpose onto this pyramid the actual ml values. S has a value of 0. There are 3 p values. They range from +1, 0, and -1. It doesn't really matter if you put the plus or the minus on either side. I'll try and be consistent with my presentation though. D can have values of -2 for this box, -1 for this box, 0 for that one, +1 for this one, +2 for this one, and then likewise -3 for this F, -2 for this F, -1 for this F, etc. So essentially any box in the middle has an ml value of 0. Anything here has an ml value of -1. Anything here has an ml value of +1, etc. We notice that this applies to magnetic quantum numbers of electrons. Recall that electrons are fermions. And recall that that means they have to obey Pauli Exclusion Principle. We comment therefore that each orbital can contain up to 2 electrons. But when they are containing 2 electrons, they have to have a difference in the, they have to have some difference in their labeling, so they actually just differ by their spin. So they're arranged in an anti-parallel fashion. So spin is plus a half and negative a half, respectively. So in the 1s orbital, we can have 2 electrons. So we have 2 groups in the s block in the periodic table. In each of these p orbitals, we can have 2 electrons. So that's 6 total, 6 electrons total. We have 6 groups in the p block. In each d orbital, we can have 2 electrons. That's 10 total, so there's 10 groups in the d block. And then finally, we can have 14 electrons in the f block. Okay, so next we're going to write a summary down of what we've seen so far with quantum numbers. Okay, so this slide, we're going to summarize the allowed values of quantum numbers for a 1 electron atom. Why a 1 electron atom? Essentially, the quantum mechanics that we look at in general chemistry is exclusively, well, not exclusively, but the ones that we'll at least look at in these videos are looking at 1 electron atoms. Consequences, nuances happen when you have more than 1 electron. So commenting that it's 1 electron atom is just more for good record keeping than anything else. Okay. We're going to consider just principal quantum number 1, 2, and 3. We've got principal quantum number. We'll look at the orbital angular momentum quantum numbers. By definition, L is 0. For an s orbital, and you start the periodic table in period 1 in the s block, so it makes sense that we'd have s. We know from our previous pyramid diagram that ml is 0 when L is 0. This vocab word here, degenerate just means same energy, or at least the way it's used here, it means same energy. So number of degenerate states per L, number of states for a given subshell L that's the same energy. Well, there's only 1. Number of degenerate states per given energy level, N, is also 1. For shell 2, or energy level 2, we'll look at your periodic table. If you go right across your periodic table, you'll notice that you can have, there's only 8 elements, and they're either in the S block or the P block. So if they're in the S block, L is 0. If they're in the P block, L is 1. If they're in the S block, L is 0, so the magnetic quantum number is 0. If they're in the P block, L is 1, they can have values, 3 values, remember, 3 p orbitals, of -1, 0, and +1. So 3 possible values. Just spotted I've made a tiny mistake on my diagram. Oh, no, I haven't. No, I haven't. I've missed something out. Okay, I missed this number out here. Let's continue the P and then we'll go back here. So L equals 1, it's a p orbital, which means there are 3 orbitals. They have magnetic number -1, 0, and +1. So how many are there? There are 3. So now you can really see what degenerate means here. It means that all of these orbitals have the same orbital angular momentum. So in terms of their orbital angular momentum, you can't distinguish them. Which reminds you, there's really no difference between -1, +1, etc., at least in terms of L. Let's go back now and continue this one. Obviously, there's only 1 orbital, so there's only 1 orbital. How many orbitals with the same energy for for a given n? Well, for n equals 2, there's 1 over here from the s orbital. There are 3 over here from the p, so there are 4 total. And then finally, to go over to n equals 3, well, in period 3, we can have s and p orbitals again. So we can duplicate this column. We can have an s orbital, L equals 0. Therefore, we have ml equals 0, and there's only one of them. We can also have p. So we just duplicate this. 1, minus 1, 0, plus 1, 3. But now we can also have d orbitals. We know that there are d orbitals that have the designation n equals 3. And we know for a d orbital, L equals 2, and there are 5 values. There are 2L plus 1 values, so there are 5 of them. And they range from minus 2 plus 1 is minus 1, minus 1 plus 1 is 0, etc., up to positive 2. So there are 5 values. And then we have 5 plus 3 plus 1. So that's 9 values, degenerate values, or at least the same energy in terms of n. So this is a nice summary of what we've encountered so far, at least for sp and d orbitals. So on this board, there's a couple of things that we're going to look at. We're going to look at penetration of the nucleus based on the orbital angular momentum quantum number L. Before we do, we're going to introduce something that's new, and it's an interpretation of the wave function psi that was given to us by a well-known physicist and a pioneer in quantum mechanics called Max Born. It seems like every pioneer in quantum mechanics was called Max, but there you go. So Max Born had a massive insight, and he said, well, trying to conceptualize what this new quantum mechanics could mean, he said, and to this day we still believe, that the wave function, although the wave function has no physical meaning, it's a mathematical abstract notion, it has no physical meaning, the wave function squared does, and it represents the probability of locating the fermion, or the particle. So our particle here is just the electron. So whenever we see psi squared, and we assume that psi refers to the electron wave function, we assume it's the probability of locating an electron. So that, therefore, it makes sense to plot psi squared rather than psi. And if we plot psi squared for a 2s electron versus a 2p electron, so we're not allowing the energy to change. We have principal quantum number equals 2. The only thing we'll allow to change is the orbital angular momentum quantum number L. So we have L equals 0 here for the s orbital, and L equals 1 here for the p orbital. So I'd ask you to recall this table here, where we have the sharp, principal, diffuse, and fundamental orbitals that we know from the periodic table. Okay, so if we look at the probability of locating an electron, where 0 distance on this x-axis here represents the nucleus itself, and we can go out a distance r from the nucleus, then we see that overwhelmingly the nucleus is most probably, the 2s electron is most probably in the nucleus itself. So the area under this curve, you are most likely to find the 2s electron at the nucleus, whereas strikingly different, if you're a 2p electron, you have 0 probability of being located at the nucleus. So we know that s electrons can penetrate the nucleus, and we'll see why. It's essentially because they have 0 orbital angular momentum. Okay, so let orbital angular momentum let's call it capital L. So orbital angular momentum, capital L, is going to be our quantum number L plus 1, all square rooted, multiplied by h bar. H bar is just a tack on units. Remember, h bar has units proportional to joules. So for s electrons, that's what we're going to use. For s electrons, L equals 0. So the big orbital angular momentum is going to be 0, 0 plus 1. Now we have a product here that has a 0 in it, so it's going to kill the whole term. So there's absolutely no orbital angular momentum because L equals 0. So it's blind to the nucleus, and the nucleus is blind to it in terms of any momentum signature. So because this value is 0, the s electron can penetrate the nucleus. For p electrons, obviously L is 1. So L is 1, 1 plus 1, h bar, which is 1, multiple of h bar. So here we're just setting units of h bar. So clearly you are noticed by the nucleus and you can no longer penetrate the nucleus. So this slide, there's a lot of drawing involved, so I've written it a priori so we can look at it. So if we look at orbital angular momentum, we said in the previous slide that the big L orbital angular momentum of the system is small l, L plus 1, all square rooted multiples of h bar. Well, I recall from a previous video where we looked at black body radiation that h bar is just Planck's constant h over 2 pi. And this is tacked on here. H bar and h both have units of joule second, so it just gives units to L. If we consider L equals 1, so a p orbital, then we just put 1 into this equation, and we get a value of 1.41. I think in the previous slide I said it was 1, but if you plug it into a calculator, it's actually 1.41 multiples of h bar. So if we plot that down, so we draw a semicircle here, we have plus 1.41 and negative 1.41, but our quantum numbers can only take whole number integers. So we can see that on this semicircle, we'd have to drop a bit down from the maximum to get plus 1, drop a bit up from the minimum to get negative 1, and then we can connect the origin 0 to those lines. And essentially, this is a two-dimensional way to show this precession. So essentially, at this angle, the information, the quantum piece of information would precess. We don't look at the precession in general chemistry, but there would be a precession, a cone would be outlined. And these are the three values that we've seen previously for our magnetic quantum number. Likewise, shift into a d orbital where L is 2, plugging it into this equation, we get 2.45 multiples of h bar. So we can plot that from plus 2.45 to negative 2.45. Again, our quantum numbers can only have whole number integers. So we drop it down a bit, drop it up a bit to get plus 2, plus 1, 0, negative 1, negative 2. And again, we would have each of these angles, they would circle out a cone of different angles. And and they would be the 5 values from magnetic quantum number. And we're coming up on the hour, so that will conclude this video. And we'll be back with more videos on quantum mechanics for general chemistry.